So it says recording is about to start. You're recording. Okay, so it says I'm recording. Well, let's take a look. I'm going to get out of this and get back to Chemistry 102. And we're going to start over here, and we're going to walk through that summary of reactions, again, that is on page 406 in your book. So the first one we'll talk about is a hydrogenation reaction. So a hydrogenation reaction is as follows. So hydrogenation, okay? So a hydrogenation reaction is when you take an alkene. So we'll take an alkene, we'll make this alkene. So this is called 1-butene, and it could be any alkene, but we'll take 1-butene, and then we treat that with hydrogen, and then we need a metal catalyst, and we can use palladium, platinum, or nickel. Not in the combination, just one of these as a metal catalyst. And so you could just write palladium, you could just write platinum, and you could just write nickel. And what happens is you end up adding a hydrogen, and you add a hydrogen at this carbon and at this carbon, each carbon of the double bond. And when you do that, I'll leave those there. What happens is that you end up converting an alkene to an alkane like that. So then you would end up with butane. All right. So that's the first reaction. The next one is a hydration reaction. So a hydration reaction. Okay. And for a hydration reaction, you have to know what's called Markovnikov's rule. Let's take the example of 1-butene again. So we'll start with our alkene. So again, this is 1-butene. Okay, and the way that you do a hydration reaction is you add water to a molecule. Now, how do you do that? You use water and acid, a little bit of acid and water. So it can be written several ways. You can write H3O plus, you can write H plus and H2O, but the idea is that you need some kind of acid, right, which is represented by a proton or a hydrogen cation, and water. Now, you need to know what's called Markovnikov's rule. In Markovnikov's rule is that the rich get richer, right? The rich get richer. So what that means, if you're like, what are we talking about money here? No, if you look at the two carbons involved in the alkene, I have one carbon here, one carbon here. This carbon only has one hydrogen, whereas this carbon has two hydrogens attached to it. Now, when we're adding water, when we add water to the molecule, we can write our water out like this, H2O. Okay, so one of those carbons is going to take the hydrogen, and the other carbon is going to take the hydroxyl. The carbon that has more hydrogens attached to it is the one that's going to take this hydrogen right here. Okay, so let's count. This one has 2. This one only has 1. What's a higher number, 2 or 1? Well, 2 is a higher number. And so that carbon, that carbon is going to be the one to take the other hydrogen. So now it will have 1, 2, 3 hydrogens. And the other carbon is going to have the hydrogen, but it's going to take the hydroxyl like that. Okay. Now, I would never write the compound like that. I think that's kind of ugly. I would write it like this. So I would have 1, 2, 3, 4, and I would write it like this. So this is called 2-butanol. No, we haven't learned how to name alcohols yet. But anyhow, give me a thumbs up if you follow me on Markovnikov addition of water. The rich get richer. Okay. Well, if you understand it, let's try another example. Okay. What if I had this compound? Okay. This compound right here. This is called 1-methyl cyclohexene. Okay. If I was to treat this compound with acid and water, and I'm going to write it out like that, I'm going to label those two carbons. I'm going to make one of them blue, and I'll make the other one red. Which one of those carbons is the hydrogen going to be attached to when I draw my final product? The red or the blue?
The blue one?
No. Right? What was the rule? The rule was the rich get richer. That means the carbon that has the most hydrogens attached to it takes the hydrogen, right? If you look at the carbon that I have highlighted in blue, it has 0 hydrogens attached to it. None, nada, nothing, okay? The one that's in red has 1 hydrogen attached to it. Okay, so that is the carbon that's going to take the second hydrogen, right? Like this. The other carbon, this one here, is going to take the hydroxyl, like that. And so I end up with this compound right here. And I'll draw the bond line structure beautifully. Okay. Does that help a little bit more?
Yeah, that makes sense.
Okay. All right.
Thank you.
Richer. And that's Markovnikov's rule. The next reaction is called a halogenation reaction. So that is just adding a halogen to an alkene. So let's take a look at a halogenation reaction. So halogenation, okay? And that is where we take an alkene, okay? And I'll use 1-butene again, and we treat it with chlorine or bromine. I'll use bromine for my example, so we treat it with bromine. And bromine is a diatomic element. You should know what the diatomic elements are. They are bromine, chlorine, iodine, fluorine, nitrogen, oxygen, and hydrogen. Okay, there are many ways that students memorize these. Have no fear of ice cold beer. There's Brinkelhoff that students like sometimes. Another one of my students, this guy that used to wear a hat with a big hot leaf on it, he told me I have one, and I was like, oh boy, what's this going to be? And it was, I bring cookies for our new home. Okay, so there's all kinds of acronyms that are out there, but that means that when you have bromine or chlorine in a pure sample, right, not attached to any other atoms, they exist as Br2 and Cl2. Okay, so we take bromine, and then we're going to add one bromine to one carbon of the double bond and one bromine to the other carbon of the double bond. So let's write it our skeleton, 1, 2, 3, 4, and then we're going to put one bromine here, and we're going to put another bromine over here. And so this compound would be 1,2 dibromo butane. All right, because we have a total of 1, 2, 3, 4 carbons, so it's a butane derivative. That's halogenation. All right. The next reaction is hydrohalogenation, and hydrohalogenation also follows Markovnikov's rule. So let's write it down. Hydrohalogenation. And the way that hydrohalogenation works, let's use our 1-butene again. If we react this with HBr or HCl, so I'll put here HBr or HCl, so not HF and not so HBr or HCl is usually used. Let's pretend we're using HBr in this example. Okay, the rule is the rich get richer. That's Markovnikov's rule. Markovnikov's rule, okay? So if I highlight these two carbons, if I highlight one in yellow and one in green, which one of these is going to take the hydrogen from HBr? The green or the yellow? Yeah, it's going to be the green one because the green one has two hydrogens, right? And if you're like, didn't you do the same thing before? I did, right? This carbon has two hydrogens. This carbon has one. What's a bigger number, 2 or 1? 2 is a higher number. And so the final product is going to have 1, 2, 3, 4 carbons. Now we're going to have 1, 2, 3 hydrogens here. We still have this hydrogen, and now we've added the bromine. Okay? And so that is the same thing as 1, 2, 3, 4 as 2. This is 2 bromo butane. You want to do another example? I do. Let's try if we had this compound. Okay, this is called methylene cyclopentane. If I was to take this compound and treat it with HCl, okay, if I highlight one of the carbons in green and one of the carbons in yellow, which one of these is going to take the hydrogen from HCl in my hydrohalogenation reaction?
The green.
Absolutely, because the green one has, the green carbon has two hydrogens attached to it, and this one has no hydrogens attached to it. What's a higher number, 2 or 0? 2 is a higher number, and so our final product is going to look like this, okay? Now instead of 2 hydrogens, we're going to have 1, 2, 3, And on the other carbon, we're going to have the chlorine attached. And that is the same thing as this molecule, which is, oops, that's kind of an ugly bond, which is 1-chloro, 1-methyl cyclopentane. Hydrohalogenation. All right. What else? We have the reactions of benzene. So the first one is halogenation of, halogenation of benzene. Sorry. So now we're kind of switching gears, and we're talking about reactions of benzene. So reactions of benzene. Right. And before we were looking at reactions of alkenes, so I should maybe clarify that. So these were reactions of alkenes. Okay. And again, now we're looking at reactions of benzene. Okay. So the first one is halogenation. Halogenation. And benzene is actually quite an unreactive molecule. Okay. If you take this molecule, right, this is cyclohexane, okay, and you treat this with bromine, okay, if you just treat it with bromine, you're not going to get any reaction. So no reaction, okay. If I treat it with this molecule, okay, this is cyclohexene, and I treat it with bromine, Br2, right, I get a bromination reaction, okay, where I add 1 bromine on each carbon of that double bond. But if I take benzene, okay, so this is benzene, is when you have 3 double bonds in your ring, so benzene. And I found that this summer, a few students confused cyclohexane and benzene. Okay, cyclohexane has no double bonds in it, and benzene has 1, 2, 3 double bonds in it. They're very different molecules. And when you take benzene and you treat it with just bromine and nothing else, you get no reaction. Nothing happens. You're like, well, that's not what you said in the slide. What happens is if you take benzene, and you treat it with bromine, and you also use FeBr3. FeBr3. This is iron 3 bromide. Okay. If you treat it with bromine and iron 3 bromide, then you have what's called a substitution reaction. And what that means is you'll replace one of the hydrogens on benzene, you'll exchange it for a bromine. You'll put a bromine there. And if you're like, well, aren't there 2 bromines here? Yes, there are. So what happens to the other bromine? The other bromine is going to combine with that hydrogen to make HBr. So you end up with a bromine substituted on your benzene ring, plus you end up with HBr. Okay, now these have nothing to do with the reactions of benzene. I just put these in there for clarification purpose. Okay, so that's a halogenation of benzene. The next one is sulfonation. So sulfonation, write that down. Sulfonation. Okay, and a sulfonation reaction is as such: you take benzene like this, okay, and you treat it with sulfur trioxide, SO3, and then you also treat it with concentrated H2SO4. And what that does is it adds this group, okay, which is this, okay, and this is actually a new functional group. So you end up with this compound here. This is called benzene sulfonic acid, and you also end up with water. So a new functional group for you, new functional group is when you have R and then you have SO like this. This is called a sulfonic acid. All right, so that's sulfonation. And then one of the last reactions that we want to look at with benzene, is the last one with benzene, sorry, is nitration. So a nitration reaction. Nitration. Okay, and that is where we take benzene. If you have your microphone on, could you turn it off, please? All right, so nitration plus nitric acid, HNO3. And then we also treat that with concentrated sulfuric acid, so it's really strongly acidic conditions. And in our book, it says anywhere between 50 and 55 degrees Celsius. You have to warm it up a little bit, and you end up with this compound. You end up adding a nitro group, okay? So NO2, and this would be called nitrobenzene, okay? And you also end up with water. So that's a nitration reaction, and we can throw that in here. New functional group. If I didn't mention it in the videos, I can't remember if I did or not, is when you have R with NO2, that's called a nitro group. Nitro group. All right, so that's kind of a summary of all of the reactions of alkenes and the reactions of benzene. If you're looking at page 406, you'll notice there's one other reaction in there, and it's called the addition polymers of alkenes. And I'll just show you. We don't focus on polymerization reactions a lot, but you should have an idea how polymers are made because they're so ubiquitous in our everyday life. It says addition polymers of alkenes. How do you make what's called an addition polymer? What you do is you start with an alkene, and it says if you have a generic alkene like this, they're putting a tetrasubstituted alkene like that. All you have to know how to do is that you're going to start with a lot of this molecule, maybe Avogadro's number, probably more. And then the way that you draw the polymer, I'll teach you, this is Mr. Deon's patented method. It couldn't get any simpler, okay? All you do is you eliminate the double bond, and you eliminate those bond angles. Let me show you what I mean. You start by drawing a straight line like that between these two carbons. And then instead of putting the R groups up at an angle, you put them straight up. R, 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 and R. Okay? Then what you do is you draw another line out from each side like this, put the whole thing in brackets like this, and then you put a subscript N. And that means that you're starting with N of this alkene, and N could be, and you're like, what's N? Any number. Could be 2, could be 2 billion, could be 2 moles, could be 10 million moles. I don't know. And then you end up linking all of those alkenes together to make your polymer. So this is a polymer. And things like nylon or saran, which is found in saran wrap, or polyethylene terephthalate, which is found in garbage bags. What else? I don't know. Did I say nylon? Mylar, Teflon. These are all polymers that are made using this kind of chemistry. All right, so that's a recap of the different reactions that you need to know. And we've looked at Markovnikov addition. And there we go. So I'm going to open it up to you guys. If there's any questions or anything that you want to look at, I'm happy to do that. Any nomenclature questions, anything at all?
Hey, Mr. Deon.
Yeah.
Hi. I had a question regarding when there's multiple, let's say, sorry, it has to do with naming. So let's say that you have a nitrobenzene. So you have that nitro functional group, but then you also have like another functional group on the benzene ring. What I'm wondering is, how do you know which one to use? Because in some of the examples throughout the reading, they go with the family, the historic names as the main part, and then some they use the
right.
So I'm just curious, which one how do you know which one takes precedence?
Okay, well, you have to know the common names of some aromatic compounds, okay, in order to name them properly. So let me show you what I mean. And again, this is covered in the videos, but there's common aromatic compounds that you have to be aware of, just common names, okay? And those are, so if you have a benzene, right, that's just a plain old 6-membered ring with 3 double bonds like that, that's called benzene, okay? If you add a methyl group on that, I mean, you could call it methylbenzene, but nobody does. It has a common name, and that common name is toluene. Toluene, okay? If you have a hydroxyl on there, You might think, oh, I'd call it benzene alcohol or something like that. No, okay. If you have a hydroxyl on it, there's a historical name for that, which is phenol. If you have an amino group on there, you have an amino group, that is called aniline. Aniline. If you have a methoxy group on there, so if you have OCH3, so that's called a methoxy. This is called anisole, like that. What else? Other ones that you have to know are benzoic acid. So if you have a benzene ring with a carboxyl group from a carboxylic acid, I'll abbreviate it CO2H. That's benzoic acid. And another one that I think is important for you to know would be benzaldehyde. So if I have an aldehyde directly attached to my benzene ring, like this, I'll just draw out the whole structure. This is called benzaldehyde. Right here, benzaldehyde. And so you have to be fully aware of all of these, okay? You have to be fully aware of all of these. And so if you were given a compound, like let's say you're given something that looks like this, okay? If you're asked to name a compound like this, okay, where you have a methyl group and a chlorine on it, like that, well, you have to look for a common root, if there is one. Now, not every example I'm going to give you is going to have one, but you should notice that there's an aromatic ring with a methyl group attached to it. That is a toluene. And so we can name this molecule as a toluene. Now, where the substituent is, where that methyl group is, we're going to assume that since we're calling this some kind of toluene, that this is going to be carbon number 1, the carbon that has the methyl group attached to it, right? You can assume that all of these groups, if you're naming a compound, a phenol, an aniline, an anisole, a benzoic acid, or a benzaldehyde, where all these substituents that I have in yellow are, you can assume that that's carbon number 1. And so this compound, when I name it, its proper name would be 2-chlorotoluene. Okay, let's take a look at another example. Let's say I had something that looked like this, okay? Let's say I had something that looked like this. I have 1, 2, 3, and I have a hydroxyl here, and I have this over here, okay? A nitro, there is such thing as nitrobenzene, but a nitrobenzene, that's not one of the common names that I ask you to have, okay? You have to memorize all of these that I have highlighted in yellow right now, okay? So memorize all of these, okay? But what's a common root that we do see here that's in this police lineup is this molecule right here, phenol, okay? And again, we're going to assume that the carbon that has the hydroxyl attached to it is carbon number 1. So we would number this 1, 2, 3. And so this molecule would be 3-nitrophenol, like that. You want to try another example, Joni? What if I throw one at you? What if I gave you this compound? Could anybody tell me how to name this compound? And I see that Taylor wants to take a look at question 41. So while you're thinking about that name.
Could I take a guess?
Go for it. This is the land of the free.
Is it 4-ethyl amylene?
Absolutely. 4-ethyl aniline. Okay. And the reason that the student knew that is because she said, okay, well, I have this piece right here. Hey, that looks a hell of a lot like aniline to me. And it is. That's an aniline. And so, again, we assume that the carbon that has the nitrogen, 1, 2, 3, 4, and here we have an ethyl group. There you have it, folks. That's all there is to it. So this would be 4-ethyl aniline. Okay. Perfect. Does that help, Joni?
Yes, it does help. I was just curious, will we ever get any where so the ones where you have highlighted in yellow for memories, will there ever be 2 of those on the same benzene ring?
Probably not. Probably not. I can't think of any examples where I try to do that to students, okay? And there are common names for compounds that do have both of those. For example, let's see here. For example, if I had this compound, and this is not one of the ones I expect you to memorize, it is in the book. But if you have something like this where you have a phenol and a toluene kind of thing in the same molecule, this is called cresol. So this is called para-cresol. All right. Anyhow, I'm gonna, before I answer that question, I need to stop sharing my screen just for a second and get a new blank document. Let's see here, stop presenting, go to application, here we go. All right, just give me 2 shakes of a lamb's tail here, and I'll find a new document. So question 41, we'll take a look at that. Da-da-dee-da-da. Here we go. Nope, not what I meant to do. Come on, save to files. Chemistry 102. Save. Keep both. Okay. Let me go back here and share my screen. Come on, share. All right, can everybody see my screen now? It should be pretty blank.
Yep.
All right, great. Thanks for telling me. Perfect. Okay, so Taylor wanted to look at question, what was it, 41? It says draw a condensed formula for each of the following compounds. You know what, Taylor? I don't care about drawing condensed formulas, okay? It's important that you can recognize a condensed formula. Let's just take a quick peek at these. I'm more concerned that you can draw a bond line structure or that you understand structure, but 11.41a says 2-methyl-2-hexene, the 2-methyl-2-hexene. The important thing is that when you're drawing alkenes, okay, when you're drawing an alkene, and we know this is an alkene because the suffix here is -ene, you can't condense a double bond. You always have to show a double bond or a triple bond when you're condensing, okay? You can't eliminate those like you can single bonds, right? Single bonds, we just get rid of those like crazy. So first, let's start by drawing the compound out. And this compound has a carbon chain that has 6 carbons in it. So we'll start with that. So we have 1, 2, 3, 4, 5, 6. At carbon 2, we have a double bond. So we go 1, 2, then we have our double bond. And then on carbon 2, we also have a methyl group. Let me just tidy that up. There we go. And we have a methyl group here. So Taylor, do you agree with me? Does this look like 2-methyl-2-hexene to you? Does this seem reasonable to you? Okay, good. All right, now let's think about how we could condense it. All right. Well, we have 2 methyl groups here, right? CH3 and CH3 here, and then we have this carbon. So we can start with this. We can say we have a carbon and we have 2 CH3 groups. We can put that in brackets. Now remember, I told you that you can't condense the double bond. So you have to show that. Oops, no, not that way. But then you have a double bond like this. And then here you have a carbon with a hydrogen attached to it. So we'll say CH. What are the next things that follow? We have a CH2 and a CH2. So we'll put those 2 in brackets. That will really condense things. So we have 2 of those. And then finally, we have a methyl group like that. That's the best way to condense that. You can't condense it any further, really. Okay. A couple of just kind of bookkeeping things here that I've taught this class enough to know that students sometimes think of these questions. You see how right here, I wrote my CH3 like this, and then here I wrote it like this. Sometimes I've had a student say, does it matter if you write it backwards or forwards? The reason I write it like that is because I like to indicate, you know, if I wrote this, that's perfectly acceptable, okay? Then my bond there, that's perfectly reasonable The reason I like to write it the way that I had it is because I like to indicate that the carbon is attached to the carbon, okay? So that's just a personal preference. All right, anyhow, let's try the next one, which is trans 3-heptene. So B is trans 3-heptene. And hopefully you know the difference between a trans alkene is when your two R groups are on opposite sides. So this is trans. And when the two R groups are on the same side, like this, we call this cis. So we have trans 3-heptene. So let's start by drawing our carbon chain, which has 1, 2, 3, 4, 5, 6, 7 carbons in it like this. On the third carbon, we have a double bond. So 1, 2, 3. There's our double bond. I can make that look a little better. There we go, like this. And is that bond trans? Let me ask you, is it trans? Can anybody tell me? Does that look like trans to you? Yes or no? Yeah, absolutely. So Fernanda says, yes, it's trans, right? I have the hydrogens on opposite sides. So this is trans 3-heptene. If I had drawn, and it's not asking, if I had drawn this 1, 2, 3, 4, 5, 6, is that too many carbons? What am I doing here? 1, 2, 3, 4, 5, 6, 7. If I had drawn this, this would be cis 3-heptene, okay? And that's not what we're talking about. We're talking about trans 3-heptene. So how do I condense that structure? Well, let's see, okay? I have a methyl group here, so I'll start with that, CH3. Then I have a CH2, CH2. Then I have a CH, okay? Then I have my double bond. I can't condense that. I have another CH, right? This one here. Okay, then I have 2 CH2s. So I'm going to condense those like this. And then on the end, I have a CH3 like that. And that's the best condensed structure that I can come up with. And if you notice, the condensed structure for cis 3-heptene, when you condense it, you don't show cis or trans, right? You don't reveal that. And so you get the same thing. All right. Another thing that's really annoying to me right now to keep saying, and I just want to remind you, is that when you have a CH3, that's called a methyl, right? When I have a CH2 sandwiched between two R groups like that, that's called a methylene, methylene. And when you have a CH and you have 3 R groups like this is called a methyne. Methine. So a methyl, a methylene, and a methine. It just gets kind of tiresome to keep saying a CH3, a CH2, right? Methyl, methylene, and methine are much faster. All right, let's try one more from that 11.41. Which one should we do? Taylor, do you have a preference for any of them? C, D, or E? I'll try any of them. D. Okay, let's do D. So it's cis 2-chloro-2-methyl-3-heptene. So D is, I'm going to have to look over here, cis 2-chloro 2-methyl-3-heptene. 2-methyl-3-heptene. All right, so first let's start by drawing the bond line structure. That is definitely the easiest way to attack these problems. Okay, so let's start with a 7-carbon chain. 1, 2, 3, and we're going to have our double bond. 1, 2, 3. Let's see. I'm going to need more room here, aren't I? 1, 2, 3. There's our double bond. It's a cis double bond, so we're going to start going over here. 1, 2, 3, 4, 5, 6, 7. Right, and that is cis. Right, it might not be pretty, my Apple Pencil, but those two hydrogens are on the same side. So that's a cis 3-heptene. Now what do we have to do? We have to put it in our substituents. On carbon 2, we have a chlorine, and on carbon 2, we have a methyl group. And so we'll put another methyl group here like this. Okay? So cis 2-chloro-2-methyl-3-heptene. Okay, so my structure looks reasonable. We're going to start on this side right here, and we're going to condense this. So I'm going to start with this carbon right here that I'm highlighting in yellow. And I'm going to take that and attached to that carbon, I'm going to have a chlorine and 2 methyl groups. There's a few ways that you could do this. I mean, I'm not that fussy about it, but you could put CH3, 2 of those, and then a Cl like that. That will work. Another way that I think is a little bit more elegant would be to actually draw a line, draw a bond like this to the chlorine, okay? Then after that, we have a methine and a methine. So we'll put both of those and our double bond like that. Then we have 1, 2, 3 methylenes. So we'll put methylene, and there's 3 of them. And then we have a methyl group like that. So that's the way that I would do it. I think it's more elegant that way than trying to stick the chlorine inside. It kind of highlights the chlorine like that. Does that help, Taylor? Okay, good. All right, something I want you to keep in mind is that I am on your side when it comes to the class. I'm not against you. So you might find a question on the exam tricky. You might find a question difficult. That's perfectly okay. But remember, my job is not to try to trick you, okay? I don't sit in my office down here in my basement going, moo ha ha ha. Boy, let me write a trick question that my students can't answer. No, that would make me a jerk, okay? My job is to test you on the content, not to try to mess you up, okay? Yes, some questions are challenging for sure, but it's not to come up with a little trick or something to ruin your life, all right? Okay, is there any other questions? That was a good one, Taylor. I like that question.
Hey, Mr. Deon.
Yeah.
So I was just curious, since Taylor brought up this. So every time can you assume that every time that you see a one-line structure with a double bond, that if it's kind of like a normal zigzag going from left to right with a double bond in it, that would probably be trans every time, a trans alkene?
I'm not sure exactly what you're saying, but let's revisit the definition of cis and trans, okay? So if you have a double bond, okay, when you have R groups that are on opposite sides of the double bond, that's trans, okay? If you have groups that are on the same side of the double bond, that's cis, okay? And here you can see clearly in the structure that I've drawn, it's kind of hard for me to delete these things now, okay, after the fact. But if I doctor this up like this, right, you can see that the 2 R groups are going on the same side, right? They're both going in this direction, right? And then the 2 hydrogens, right, I have one coming this way and one coming this way. And the same thing applies here. If the 2 hydrogens are opposite like this, that's trans. And if they're on the same side, that's cis. You can see these 2 hydrogens are clearly on the same side. So that makes this a cis alkene. Does that make more sense?
Yeah, that makes sense. What I was just curious about, like, let's say, for example, if I say 3-pentene, for example, or I say pentene, if we were to draw those out.
If you were to draw this molecule, so if you have 1, 2, well, there's no such thing as 3-pentene.
Okay.
So if I had this molecule, this would be trans to pentene, okay? And if you had this molecule, this would be cis to pentene. And so normally you have to indicate this. Now, why didn't I indicate it back with my example of why did I not say anything about cis or trans when I had 1-butene, right? Why did I just call this 1-butene and I didn't have to say cis or trans? Who can tell me? There's a good reason. There's a very good reason.
Is it because there's only one substituent group?
Yeah, there's only one thing attached to the double bond, right? Here's the 2 carbons of the double bond. There's only one thing attached. There is no cis or trans. Another way of saying it is like this. If you have a double bond, okay? If you have a double bond, and if there's ever 2 R groups that are the same on the end, it doesn't matter. The R could be anything. It could be a hydrogen, it could be a chlorine, it could be a methyl, it could be the biggest group in the universe, okay? It could be the planet Earth, okay? But if there's 2 groups that are identical on the end of an alkene, there's no cis or trans, right? Think about it, okay? We could even write it down here, no cis or trans, right? Let's look at it even further. Look at this hydrogen, Okay, look at this hydrogen and this hydrogen. I'll circle one in red. It's trans to this one, but this one is cis to this one. So there is no cis or trans. Cis or trans does not apply to a terminal alkene. Okay, if you're like, what's a terminal alkene? Is that one that's very sick? No, a terminal alkene is one that has the double bond on the end. Okay, so you see how this is right at the end of the molecule? So no cis or trans required. Cool?
Okay, that makes sense. Thank you.
All right, good. Okay, next question. Anybody? Well, would you like to try some nomenclature? Oh, 99. Okay, good. Let's try 99. It's better if you guys pick the problems because they're probably ones that I wouldn't think of. Write equations for the reactions that would produce each of the following products. So 11.99. You are in the lab. You're working as an organic chemist, right? Everybody who's enrolled in this class is pondering their life plans. They're like, I love organic chemistry so much. I should probably do that for a living. But you want to make this molecule, okay? This molecule right here. And this is called bromobenzene, okay? Your boss says, Taylor, if you could make 100 grams of bromobenzene, I'll give you $100,000. You're like, I'll get right on it, okay? How the hell would you do it? Well, we looked at this reaction this evening already. If you were to take benzene, which is readily available, and you were to treat that with bromine, you would actually get no reaction. I'll abbreviate that NR. Nothing would happen. What you need is a catalyst to get that reaction going. And the catalyst that we use is iron 3 bromide, FeBr3. We can write that in here. FeBr3 is a catalyst. Okay? And when you treat benzene with bromine and iron tribromide, you end up doing a substitution reaction, okay, where you substitute one of the hydrogens for a bromine to make bromobenzene. So checkaroo on that, okay? And you'll also end up with HBr as a byproduct. In B, they're asking us to make chlorobenzene, okay? So we would use an analogous procedure. Okay, if we want to make chlorobenzene, to do that, we would start with benzene. But instead of bromine, of course, we'd treat it with chlorine. And instead of iron 3 bromide, we'd use iron 3 chloride, FeCl3, which again is our catalyst. Okay, and that would cause the substitution of a hydrogen for a chlorine. So we'd get chlorobenzene plus HCl. The last one is the nitration reaction. I'll just remind you that in the nitration reaction, okay, we start out with, where's my pen? We start out with benzene, okay, and we treat it with nitric acid, HNO3, and then we also use concentrated sulfuric acid, and we cook that up to around 50 to 55 degrees Celsius, and that will perform the nitration. You end up with nitrobenzene plus you also produce water as a byproduct. Question 99 in the books. I was just thinking, there's probably another common aromatic compound, and it's probably good for you to know. I'll teach you something new here about naming aromatic compounds. And that's when you have a di-substituted aromatic compound. And again, this is covered in my slides. But if you have an aromatic ring, a benzene, and it has only one substituent, okay, that's called monosubstitution, right? If you have two substituents, okay, if you have two substituents on a ring, if you have X and Y, that's called di-substitution, okay? So I'm just going to erase this for now. So if we have di-substituted benzene, okay? We can have our X and Y next to each other, right? Like in a 1-2 arrangement. We can have them arranged like this, X, Y, so that they're 1, 3. So this is 1, 2. This is 1, 3, right? 1, 2, 1, 2, 3. And we can also have them 1, 4, like this, X, Y. So this is, let me move that up. Okay, so we can have X, Y, and this is 1, 4 substitution. Did anybody pick up on what the common names are for 1, 2, 1, 3, and 1, 4 substitution?
Ortho, meta, and para.
Absolutely. So when they're 1, 2, they're called ortho substituted. When they're 1, 3, they're meta substituted. And when they're 1, 4, they're para substituted. Keep in mind, ortho, meta, and para, that only works for di-substituted benzenes, okay? If you have a benzene and you've got, you've got X and Y and Z, okay? Ortho, meta, para will not work on that. Forget it. And if you're like, well, what makes di-substituted benzene so darn special? Why do they get a special, nomenclature system of all this ortho, meta, para baloney? It's because they're so common. Di-substituted benzenes are just so common that the ortho, meta, para thing has just stuck around for millennia, right? Okay, so based off that, there's one other compound I want to show you that's a common compound, and I think I did mention this in my videos, and that's when you have two methyl groups, okay? If you have two methyl groups, like this, a CH3 and a CH3, did anybody pick up what this compound is called? Got a funny name. No? Mm-hmm. Okay, so these are called xylenes, okay? So this one would be called orthoxylene, XYLENE. This one would be called metaxylene, and this one here, of course, would be called paraxylene. Okay, so it's a good idea to know the xylenes. You could put a sign by them, the xylenes. And the reason why is, I was just thinking about this, the xylenes are actually very commonly used as solvents in organic chemistry because they have higher boiling point than toluene. They're really good for heating up reactions at really high temperature. So xylenes are used all the time in organic chemistry. Where are we? Right. Let's see. The xylenes. With that in mind, let's try some more nomenclature problems. I'll throw one out there and see if you guys can name it for me. If I was to have this compound, I have could anybody name that compound? I'll give you a few seconds to think about it.
Can I take a stab at it?
All right. Go for it.
So, 3-bromo-5-chlorotoluene.
Hell yeah, you nailed it first try. Awesome. Okay, so what Johnny's saying is he's like, look, I saw the common root, which is toluene. Okay. And Greg and I were actually discussing this in the lab the other night. He came up with a really good question. And he's like, well, what if you have a tie? Right? If you start here 1, 2, 3, you'd end up with 3 and 5. And he's like, okay, well, if I started here and went 1, 2, 3, 4, 5, I still end up with 3 and 5. How do you break that tie? And the answer is you do it by alphabetical order, right? You have a bromo and you have a chloro. Well, B comes before C in the alphabet, and so this would be the proper numbering system. And so just like Johnny said, this would be 3 bromo, 5 chloro, toluene. Can I try another one with you? Could you name this molecule? Try this one. Give you a second to think about that one. Okay, Johnny put 2,4,6 trinitrotoluene. Yeah, I agree with that. Because if you look here, we have the common root of toluene. And then we would number that 1, 2, 3, 4, 5, 6. It doesn't matter if you go clockwise or counterclockwise. It's symmetrical, so you get the same thing either way. And so this molecule becomes 2, 4, 6 trinitrotoluene, like that. And the common name for this is TNT. All right, so that's the structure of dynamite, TNT. All right, let's try some other nomenclature problems here quickly. I want to see if you could name this compound. This is something they love to ask on the ACS final. Greg says, what if it were dinitrobenzene? Then you would call it dinitrobenzene. If it was a benzene with 2 substituents, then you could use orthometapara. Either one would work. Could anybody name this compound that I have right here? Again, this is a question that the ACS loves to ask. Okay, nobody has any idea about this one? Well, could anybody name this compound? Could you name this compound that's in red?
Did you see my response, Mr. Deon?
Oh, no, I didn't. Let me see here. Oh, you wrote 3-methyl cyclohexene. Damn. Okay, I'm sorry, Johnny. Okay, so I'll recap here. This is cyclohexene. And so the trap that students fall into, and you're right, Johnny, you're absolutely right, is that you know, they'll come up with all manner of answers for this question, some really strange answers. But when you're numbering the substituents on a cycloalkene, okay, sometimes they get confused on where to start. They'll go like 1, 2, 3 or something. Then they'll say 1 methyl 2 cyclohexene. No, okay. You always start by either going this way through the double bond or this way through the double bond. Your first 2 steps have to be through the double bond. Be damned about the rest of the substituents. Forget about them. The first 2 steps have to be through that double bond. Now, which way do you do it? Do you do it this way or do you do it like this? 1, 2. And the answer is you do it in such a way that you give the substituent the lowest possible number. So if I do it this way, I end up with 3 methyl cyclohexene, which is the correct number, or the correct name, cyclohexene. Okay. If I had gone the opposite direction, if I had gone 1, 2, 3, 4, 5, 6, then I'd have 6 methyl cyclohexene, which would be incorrect because 3 is a lower number than 6, and we always seek to give our substituents the lowest possible numbers when we can. Okay, so that's a trap that students will fall into from time to time. It's a real classic with ACS. Okay, so with that in mind, let's try another one. Okay, what if I gave you this compound? And this is one I'm stealing from the book. I'm looking over at the book right here. So if I had this and I have this. So could anybody help me name this compound? Okay, 2 substituents. I'll try to keep my chat open so that I can see if anybody answers. How would I name this one? This is 11.43D. Okay. Well, if you're unsure, let's take a look at how we would do that. Okay. I don't see an answer yet. And remember, the first 2 steps have to be through the double bond. I can either go this way, 1, 2 like this, or I can go 1, 2 like this. Okay, good. Thanks, Madison. I think you're pretty darn close. Okay. So we would start going this way because we always want to give the first substituent the lowest possible number. And we have a substituent at carbon 1. So we have 1, 2, 3, 4 like that. The only thing that you're missing in your answer is that this group that's shown right here, this is a tert butyl group. Okay, and so here we have a methyl group. Okay, and which one of those is going to come first? Well, we alphabetize M or B, and B comes before M in the alphabet. And so this molecule would be 1 tert butyl. Remember, tert butyl is hyphenated. 4 methyl cyclohexene. There's another thing they're trying to test you on in this question, okay? And that is alphabetizing substituents, right? It's knowing that you do not alphabetize by the letter T, right? You do not do that. You alphabetize by the letter B and by the letter M. You always ignore prefixes like dirt, not dirt, tert, sec, mono, di, tri, tetra, hexa, hepta, whatever, okay? The only prefixes that you do not ignore are iso, cyclo, and neo. And as a student pointed out the other night, they're like, I haven't even seen neo yet. So don't even stress about neo. All right? So iso, cyclo, and neo. But again, probably the only ones we'll see in this class would be iso and cyclo. All right. What else? There's another aromatic compound. Is it tert because of the 3 methyl groups? The answer to that is you have to memorize the alkyl groups. So I went over those at the beginning of the last class, which didn't get recorded. And so you would see those on page, oh, those are way back in chapter 10. So those are in my slides. I'll just write them down for you again, okay? So again, these are in the slides. You have to recognize methyl, ethyl, propyl, isopropyl, butyl, isobutyl, sec-butyl, and tert-butyl. Okay, these are the alkyl groups that you have to know. Everybody has to have these memorized, okay? So go into the slides and make sure that you're aware of all of these groups. Okay, so question number 91. 91, let me see. It's draw the structure of the following compound. Sure, let's try that. So this is 11.91, 91. And we'll start with A, which is 2,4-dibromotoluene. So A is 2,4-dibromotoluene. Well, the first thing we should do here is draw a toluene molecule, right? Because that's our common root. So we'll start by drawing a toluene molecule. Of course, the carbon that has the methyl group attached, that's going to be carbon number 1. Okay, and then we could go clockwise or counterclockwise, it doesn't matter. But at carbon number 2, we're going to put a bromine. Oops, try to be consistent here with my coloring. We put a bromine, and then at carbon 4, we're going to put another bromine. And so that's 2,4-dibromotoluene. The next one is 1,2,4-Tri-Ethyl Benzene. So 1,2,4-Tri-Ethyl Benzene. Okay, so we're going to start by drawing our benzene. And again, you can number the carbons anywhere. You can start you can start here. 1, 2, 3, 4, 5, 6. I don't care where you start. Doesn't matter. Okay. So at carbon number 1, we'll put an ethyl group. There's an ethyl group. At carbon 2, we'll put an ethyl group, CH2, CH3. And then at carbon 4, we'll put an ethyl group. So there you have it. 1,2,4-Tri-Ethyl Benzene. C is isopropyl benzene. So C is isopropyl benzene. So we just draw a benzene ring. That. And then we put an isopropyl group. An isopropyl group has 3 carbons. 1, 2, 3. So that's isopropyl benzene. If you just had propyl benzene, right? Propyl benzene, which it's not asking for, but propyl benzene also has a 3-carbon group, okay? But they go straight out 1, 2, 3. Okay, so an isopropyl versus a propyl group. And the last one is 2-bromo-5-chlorotoluene. We can just do it over here. E is 2-bromo-5-chlorotoluene. So we'll start it by drawing our toluene. Again, we'll call this carbon number 1, right? We have carbon number 1, 2, 3, 4, 5, 6. So at carbon number 2, we'll put a bromine. And at carbon number 5, we'll put a chlorine. And there you have it, done. All right. All right.
I have a question.
Go for it.
At what point do you switch from naming the compound or the molecule based on the aromatic ring versus the chain attached to it?
Oh, the only time that you would name the compound based off of the chain is when the chain has more carbons than the aromatic ring. So I can give you an example of that. So let's say we have, let's say we have an aromatic ring, right? and we have, 1, 2, 3, 4, 5 carbons off of like that. Okay, that group, we don't go over that group in gross and dirty detail. I don't mention it all the time, but you can probably imagine if you have 1 carbon, it's a methyl, 2 is an ethyl, 3 is a pentyl, 4 is a butyl. Well, this is probably a pentyl, right? So you would call this molecule pentyl benzene. Okay, you call that pentyl benzene because you have, again, 1, 2, 3, 4, 5 carbons in here. If you have a chain that has more than 6 carbons in it, so if we look at an example, if we have our aromatic ring, okay, and we have a chain, let's say, that has 1, 2, 3, 4, 5, 6, 7, 8, okay, then the benzene ring, this is not considered the parent anymore. This is now considered a substituent. And when benzene is a substituent, right, just like if you have RCH3, that's called a methyl. When benzene is a substituent, okay, when it's not the parent, when a benzene is a substituent, okay, it's called a phenyl. A phenyl, not phenol, right? Phenol is something else. Phenol is this. Is a benzene ring with a hydroxyl attached to it, okay? So this is a phenyl. And so we would number this chain 1, 2, 3, 4, 5, 6, 7, 8. And so this compound would be 1-phenyl octane. Right? Like that, 1-phenyl octane. So when benzene is a substituent, it's called phenyl. Does that clear it up, Johnny?
Yes. Thank you.
And if somebody is out there wondering, what if it's 6 carbons and 6 carbons? Okay, again, I'm not here to split hairs and give you every stinking exception under the sun. Okay, that's not my job. My job is to make sure that you understand the content. Okay, not to come up with an exam that has 50 exceptions. No. Okay, so don't stress about every exception under the sun. What else? There's something I just saw here that I thought would be fun to take a look at. Is could we name a diene? All right, if I had this compound, yeah, could you name that compound? Or we could try this one. I thought this one was kind of a good one. We have this. Could you name the compound on the left? So this is called a diene because it has 2 alkenes in it. And we would number it like this, 1, 2, 3, 4, 5. And so it's a pentadiene, and we would call this 1,5-pentadiene. The same thing applies to this molecule. On the right, we would number it so that we always have to start on a double bond. You can see that it's symmetrical, so it wouldn't matter which side we started on. I'll just start here, 1, 2, 3, 4, 5. And so this molecule would be 3-methyl 1,4-cyclopentadiene. All right, 3-methyl 1,4-cyclopentadiene, because you have a double bond starting on carbon 1 and 1 starting on carbon 5. And if you're wondering, like, so I had a student ask me this a couple semesters ago. She said, why are the locants important in dienes? Like, why do you have to have a number? The reason why is, what if you had cyclohexane, right? What if you had 2 double bonds like this? Or if you had 2 double bonds like this? These are 2 very different molecules, right? We number them 1, 2, 3, 4, right? 1, 2, 3, 4, okay? The molecule on the left is 1,3-cyclohexadiene, and the molecule on the right is 1,4-cyclohexadiene. So you can see that including those locants, the numbers, that is important. So 1, 4, and 1, 3, those are 2 very different compounds. All right, why is the one on the left 1, 5 instead of, oops, I was testing you. Who was that? Brianna? I'm testing you, and You're right. There you go. It's 1, 4. Yep, good. Has anybody learned anything in this review session? Let's see. One person says, yes. Okay, good. A terminal alkene is not dying. Good. So you've learned that. Okay, good. All right. One time I said something about dienes, and the student was like, yes, I am dying. All right. It smashed all my brain, and it will reorganize itself later. Yeah. It'll coagulate and form some solid, concepts for you. All right. Are there any other questions that you want to look at? Somebody says, how do we know which alkanes have low, high melting or boiling points? So boiling points and melting points for alkanes are based on two things, okay? So alkane melting point and boiling point is based off of two things. And the two things are size, the size of the alkane, and branching. So let's say we were comparing, okay, let's talk about size first. We'll start with size. So if we're comparing sizes, okay, if we have butane, which has 4 carbons in it, versus 1, 2, 3, 4, 5, 6 hexane, which one of those is going to have a higher boiling point? The answer is hexane, because hexane is a longer molecule, and you're going to have more intermolecular forces when the molecules pack together, right? You just have more interactions between 2 molecules of hexane compared to 2 molecules of butane, right? So it's based off of just the size. Okay, does that make some sense? I hope so. The analogy that I use for my students sometimes is this. Let me just stop presenting here for a second. And you could look at me while I do a demonstration here, and it won't be anything complicated. But has anybody ever seen Velcro before? I'm going to assume you have. If you went to Walmart and bought a piece of Velcro that's 1 inch long, right? If you've ever looked at Velcro, there are forces that hold the 2 pieces of Velcro together. It's kind of like little hooks into like a piece of like cotton or fuzz or something, right? If you had a piece of Velcro that's 2 inches long, let's say, and you pulled it apart, did that take some of your energy from your body? Yes. Yes, not a lot, but it took some. Let's say you have a piece of Velcro that's 25 feet long, okay? It's still the same forces holding the Velcro that it was in the 2-inch piece, but you'd be going shh, 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 ripping it apart and ripping it apart. Still the exact same force, but since it's longer, it takes more energy to break those intermolecular forces and to get the molecules to go from the liquid phase to the gas phase. So that is why, as chain length increases, boiling points and melting points increase. Okay? Now, with respect to compounds that have the same number of carbons, the way that you determine whether a boiling point is higher or lower is based off of branching. And let me show you what I mean by that. All the way down. Oops, did that get deleted? Okay. So it's based off branching. Let me show you what I mean. Okay. And basically the rule is this, Stephanie, more branching equals lower melting point, lower melting point and boiling point. Okay. Let me show you what I mean. Let's say you have a hydrocarbon with 5 carbons. If you're comparing pentane versus this compound, 2-methylbutane, versus this compound, 2,2-dimethylpropane, right? The branching is increasing this way. Most branching, right? And branches are just substituents. More branching and less branching. Okay. Have you ever been to IKEA before? Well, if you buy furniture at IKEA, they always try to get it to be really flat, and they find efficient ways of packing it. Think about it. If you have two pentane molecules like that, just straight old pentane, they're going to overlap really efficiently. Okay? So it's going to have more intermolecular forces, and it's going to have the highest melting point, and boiling point in this group. Let's say you had another molecule of this, which is 2-methyl-butane. You can see they might have some intermolecular forces, but they can't pack nearly as efficiently. And then if I have another molecule of this is almost spherical, and these don't pack efficiently at all. So the more branching that you have, okay, so more branching, going to be over here, we're going to lower melting point and boiling point. So the highest melting point and boiling point would be this, the lowest would be this, and then this would be somewhere in between. Does that help? Good. All right. The same thing applies for alkenes and alkynes as well. Yes, the more branching, the lower the melting point and the boiling point. Yep, absolutely. But let's say we wanted to compare the boiling point of, I don't know, say we wanted to compare the boiling point of, you know, pentane versus let's say, I'm trying to think, make this as easy as possible. Pentane, this compound, or I haven't even talked about these yet, so I think I'm getting ahead of myself. I'm trying to go into the next chapter, so yeah, we'll just stick with the alkanes thing for now, and then it's the same trend for alkenes and alkynes. Once we get into aldehydes, ketones, alcohols, then we'll look at more trends in boiling points and melting points. Does everybody know the functional groups? Did everybody practice their functional groups? If I show you a functional group, can you tell me which one it is? If I have, you know, a functional group where I have a carbonyl and an oxygen and then another R group like that, can anybody tell me what functional group this is that I have shown here? Yeah, absolutely. This is an ester, right? What about if I had this one? What if I have an R group and a carbonyl and then another R group like this? Can anybody tell me this one? This functional group? Absolutely. This is a ketone. What if I had an R group and a carbonyl? I'm addicted to carbonyls here. And a hydrogen. What about that one? We talked about it earlier. We had it in a compound, in a benzene derivative. Johnny says aldehyde. Yeah, it's an aldehyde. All right, I'm going to give you a tough one. What about this one? If I have a carbonyl and then a nitrogen, and you know, something like this. What about this one? Can anybody tell me which one this is? Kylie says an amide. Absolutely, it's an amide. Okay, I'm going to copy that. Amide. Oops, I didn't mean to do that. Paste. Try again. Copy. I put it down here. My amide. Paste. There we go. Okay. And come on. Paste. And come on. There. So now I have 3 amides. If I have 2 hydrogens attached to my nitrogen, that's called a primary amine. Okay, just like Madison said, if I have one hydrogen and one R group, that's called a secondary amine. Sorry, a secondary amide. Shit, pardon my language. I'm getting tired. And if I have two R groups, okay, then I call this a tertiary amide. Tertiary amide. Okay, so there's three classes of amides. What are some other functional groups? You would have learned this one. If I have R with a hydroxyl, what's that one called? Yeah, that one's an alcohol. Alcohol, like that. Okay, other functional groups are alkenes and alkynes, right? If you have a double bond, right, between two carbons, that's an alkene. You have a triple bond between two carbons like this, that's an alkyne. Okay, if you have a ring like this somewhere in your structure, that's called an aromatic. Aromatic. There's another aromatic compound that I had in one of my videos, and you need to know the name of it. Could anybody name this compound? What if I take a benzene and I put a nitrogen inside the ring? Did anybody pick up on the name of this aromatic compound with a nitrogen in it? It's not nitrobenzene, no. Nitrobenzene would be a benzene ring with a nitro attached. That's nitrobenzene. So if I have a nitrogen in the ring, this is called pyridine. Okay. If you look at section 11.7, I believe, you'll see heterocyclic aromatic compounds. So this is in section 11.7. Pyridine is the only one that I ask that you know. And the reason that it's important is because later on in the class, we look at more and more heterocycles, okay, which are benzene rings or aromatic compounds that have atoms inside the ring, like nitrogen and sulfur, oxygen.